let's talk about one-sided derivatives. And I think a good place to start would be to take a look at the book definition here. So, first of all, they're telling us that a function is differentiable. We can differentiate it on a closed interval, and the interval goes from point A to point B, or value x equals A, value x equals B. It's differentiable if we can differentiate it at every point on the interior, so this is A and this is B. We want to be able to differentiate it on every point between A and B. And since A kind of ends right there and B kind of ends right there, we want to be able to have a left-hand and a right-hand derivative. So my right-hand derivative would be at A because I'm coming at A from the right side, and my left-hand derivative would be at B because I'm coming at B from the left side. And to find the derivative, or whether it exists, is I just use the same old formula that we've been using, although I hate to call it old because it's always new and exciting. Except that when I'm finding the right-hand derivative at A, I use as h approaches 0 from the positive side, and then when I'm finding the left-hand derivative at B, I'm finding the limit as h approaches 0 from the negative side. Frequently that won't really make a difference, but it does make a difference sometimes, especially when you have a limit that is approaching infinity, or negative infinity. And then just like when we were talking about limits, if I have a function that goes like that, and let's say then has an open circle there, and another piece of the function goes like that, and it has an open circle there. In order to have a limit at this point here, at this point right here, you remember that the limit coming from the left and the limit coming from the right had to be the same. And it's the same thing with the derivative, because a derivative is a limit. We say that the function has a two-sided derivative, we just call it a derivative, only if the function's right-hand and left-hand derivatives are defined and are equal at that point. So now we can attack our problem with a little bit of theoretical backing. So I have this piecewise function, and I'm supposed to find out if it has a derivative at x equals 4. And as you can see, where x equals 4 is the point that marks the two different parts of the piecewise function. So the equal at that point coming from opposite sides. So I'm going to take a look at my first part of the function and find out, well, what is the derivative of that function? Are you kidding me? Well, the two different parts of the piecewise function are going to meet there at x equals 4. So let's take a look at the first part of the piecewise function, and let's find out, well, what is the derivative of that part? Now, doing this first part is going to involve just a tiny little bit of interesting arithmetic, and then I'm going to show you like an easier trick. But let's do the first part. So I know that to find the derivative of this, I'm going to use the alternate form. So I would have the limit as x approaches a of f of x minus f of a divided by x minus a. And I know that I'm looking for a is equal to 4. So I'm going to set this up as the limit as x approaches 4 of f of x, which is negative 1/2 plus 6, minus f of 4, which would be, put in parentheses, negative 1/2 times 4 plus 6, divided by x minus 4. So let's work on this a little bit. But before we work on it, I forgot my x right there. Sorry. Keep going. The limit as x approaches 4 of negative 1/2 x plus 6 minus, well, let's actually make this a plus now. So I'm going to leave it as 1/2 times 4, and you'll see why in a minute. You don't have to, you could make it 2, but it'll be a little bit easier this way. Minus 6, all divided by x minus 4. Maybe we'll come back to that arithmetic point in just a minute. The limit as x approaches 4 of negative 1/2 x, well, my 6's are going to go away, plus 1/2 times 4 over x minus 4. And here's a little bit of arithmetic that I told you about. This is the same thing as negative 1/2 times x minus 4. Think about that arithmetically for a minute. So if that is the same thing as negative 1/2 over x minus 4, and it's divided by x minus 4, as you can see, I can cross those two things out, and so the limit as x approaches 4 of negative 1/2, well, we know it's equal to negative 1/2. So that is the slope of our first piece of the function at x equals 4. I'll put it in there, negative 1/2. Now, the first thing I want to point out to you is that we did not have to go through all that rigmarole. Because let's just take a look at this piece of the function right here. This is a linear function. What is the slope of a linear function? The slope of a linear function is given to me right here. And sure enough, it turned out to be just the same. So if you're ever looking for the derivative, remember the derivative is the slope of the tangent of a function at a particular point. If you have a linear function, you know what it is. All you need to do is look at realize that this is point slope form. Y equals mx plus b. There's the slope of the function. That's definitely the slope of your tangent because it's a linear function. And avoid all of this rigmarole right here. Secondly, when I decided to keep this piece right here as 1/2 times 4. I mean, I didn't really have to do that. I could have done what really any normal person would have done and gone from here and made this negative 1/2 x plus 2. And knowing that I had this denominator, I could still have seen that I could pull my negative 1/2 out of this, and it still would have been times x minus 4. So simplifying it to 2 really wouldn't have made that much of a difference. It would have worked out the same. Just, I thought it would be a little bit easier for me to see it going this way that looks a little bit less conventional. Okay, so we've got the first part of the answer here is negative 1/2, and what I'm going to do is I'm going to clear out the board to do the second part. Now, for the second part, we really do need to approach it in the normal way. So remember, I'm going to try and find f of x minus f of a divided by x minus a, the limit thereof as x approaches a. So, and I'm working on this piece right here. So, what I have is I have the limit as x approaches 4 of 4x minus 3, that's f of x, minus 4 square root of 4 minus 3, that's our a, all over x minus 4. So I think we can work on this a bit. I have the limit as x approaches 4 of 4 radical x minus 3 minus 4 radical 1 over x minus 4. which is the limit as x approaches 4 of 4 radical x minus 3 minus 4 over x minus 4. Now here, I need to get this radical sign out of the numerator. So I'm going to multiply by the conjugate. I'm going to multiply. Actually, before I do that, I'm going to do one little thing here. I'm going to go limit x approaches 4 of 4 times radical x minus 3 minus 1 over x minus 4. Just to make this multiplication a little bit easier. I just factored out a 4 right there. So I have the limit as x approaches 4 of 4 times radical x minus 3 minus 1 divided by x minus 4. And I'm going to multiply that by the conjugate that has my radical, not forgetting my parentheses here, of radical x minus 3 plus 1 divided by radical x minus 3 plus 1. So I'm multiplying it by 1. Now I remember that a minus b times a plus b equals a squared plus b squared. And so I now have the limit as x approaches 4 of 4 times, well, this would be x minus 3 because that times that squared minus that squared 1 divided by x minus 4 times radical x minus 3 plus 1. Well, because I left my denominator in factored form like I've been encouraging you to do so you can kind of see how it plays out. Because if I look at my numerator now, I have the limit as x approaches 4. Well, 4 times x minus 3 minus 1, there should be another parentheses there, is the same thing as 4 times x minus 4 divided by x minus 4 times the square root of x minus 3 plus 1. And what do you know? By leaving things in factored form, I get rid of that x minus 4, which solves our problem of substitution. Because you can see, if I was just to have substituted 4 in there, I would have had the indeterminate case of 0 over 0. But now I don't. Now I have the limit as x approaches 4 of 4 divided by the square root, I said divided by the square, divided by the square root of x minus 3 plus 1. Now I can substitute in 4, so that is equal to the limit. Well, I'm going to substitute in 4. So that is going to equal 4 divided by the square root of 4 minus 3 plus 1, which is equal to 4 over 1 plus 1, which is equal to 2. So now I have found that the derivative of my second piece right here, so my first piece was negative 1/2, and my second piece is 2. So since I have different derivatives, the derivatives are not equal, then I can find out that this piecewise function here cannot have a derivative of x equals 4 because the derivatives of either half are different. And just so you can see what this looks like graphically, because this problem really you need to be able to solve it both graphically and algebraically, you can see that at the point, I'll try and make you see it, at the point x equals 4, right down here, whoops, that would be this joining point right there, and clearly the two pieces of the function have different slopes. So they do not have the same derivative, so you cannot say that they have a derivative because the left and the right are not the same.